Section 4.1, Probability Distributions. When we're talking about probability distributions, we're talking about the occurrence of something happening. We've talked about this already, such as rolling a die. There's a 16% chance, 16.67% to be 1 or 2 or 3 or 4 or 5 or 6. I want to talk about in more details how these results are distributed. Now, we'll use the term discrete and continuous. A random variable is something as a result. We don't know what it's going to be. The variable is discrete if there's only a finite number of outcomes. For example, there's only 6 outcomes when rolling a die, a 1 through a 6. There's only 2 outcomes flipping a coin, a heads or a tails. So that is discrete. A continuous is there's an uncountable number of outcomes. We can use a number line to look at this. Now, number of calls made by a customer, service center, you can only have so many calls. You can't have 3.5 calls. You have 8.2 calls. You have 1 call, 2 calls, 3 calls. You cannot have a decimal amount. Now, so that's discrete. That is the finite number of outcomes. You're giving 0 to 10. Like I said, flipping a coin is 1 heads or 2 tails. Number of calls made. You can make 1 call, 2 calls, 5 calls. Now, continuous, as important, is uncountable. That includes decimal points. You could have 3.3 calls, 1.2, 15.5. On this number line, I've got about 12.5. So we can have an infinite result, and that includes decimal points ad infinitum. That is continuous. This example is I could ask someone at a furniture store, how many chairs are there? And they could give you a count, 15, 12, 225. That would be discrete. Continuous would be of all the furniture stores in the United States, what's the average number of chairs? And I could say 55.3 when I add them all up, divide by the number of stores. And that is continuous. Now, here's some examples here. Which of the following are continuous or discrete? Number of calves that cows give birth to in a year. That's discrete. A cow can only give birth to 1 calf, 2 calves, 3 calves. It's a finite number. The speed of a rocket. Well, that's continuous because that could be 2,000 miles an hour, 2,000.21, 3,000.862. It could be any number. The number of days of rain for the next 3 days. Well, when we're talking about rain, either it rains or it doesn't rain. So in this case, we're looking at did it rain 1 day, whether it's for 10 minutes or all day, or did it rain 2 days or rain 3 days. So that is discrete. Now, discrete probability distribution rests on each possible value can assume within its probability means the probability is at the lowest, 0% up to 1 or 100%. And all the possible probabilities will only add up to 1. And the sigma on the right there next to the P is the summation. It's 1. And when we're talking about these probabilities, we're talking about as a group total. What's the possibility of rolling a 1 is 16.67% on a die, or 2. These add up. When I add the 16.67% for each of the 6 die, that adds up to 100%. Now, if I wanted to construct a discrete probability distribution, let me go through this here, and I'll go to the next page then. You want to make a frequency distribution of all the options I'll show you. You want to find the sum of all the frequencies. You want to find the probability of each possible outcome by dividing its frequency by the sum frequencies. And the total should be add up to 1 or 100%. Here's an example here. And I've got the results on the left and how we calculate it on the right. Suppose I have an industrial psychologist. He's evaluating 150 employees and rates them from 1 to 5, where 1 is extremely passive, 2 somewhat passive, 3 is neutral, 4 is somewhat aggressive, 5 is extremely aggressive. And these are not good or bad terms. As I explained in the class, extremely passive could mean that's what we want in customer service. We don't want someone who's got a customer calling in and someone who's passive helps them. Someone who's aggressive is going to yell at them, we're going to lose a customer. On the flip side, extremely aggressive is a person in terms of sales. They're not going to give up. They're going to keep going after it over and over. So it depends on what the position is, but that's why you have these types of analyses. So we have, or say this psychologist has evaluated 150 employees based on the scores 1 through 5. And number 1, extremely passive, has 24 individuals. Number 2 is 33 individuals. Number 3, which is neutral, 42 individuals. 4, somewhat aggressive, 30 individuals. And 5, extremely aggressive, 21 individuals. So that was on the left. What I've done on the right here, you've seen I've got those same numbers in the first 2 columns on the left, on the right box that is, with the scores and the individual number of scores. It adds up to 150, total number of people that were surveyed. But then I take a fraction. 24 out of 150 is the number of people that scored a 1. 33 out of 150 is scored 2, and so on and so forth. So we've got that probability by fraction, and then I put by decimal. 24 out of 50 is 16%. 33 out of 150 is 22% or 0.22. 42 out of 150 is 0.28 or 28%. 30 out of 150 is 0.2 or 20%. And 21 out of 150 is 0.14 or 14%. When I add all these up, this adds up to 100% or 1. Now, I've got 2 sets of data here, and I want to know if they're actually properly developed here in terms of their true probability tables. On the left, it doesn't matter what the x is, but what I'm looking at here is the probability of where x equals 5 is 1/16. Probability 6 is 5/8, which is 10/16. Probability of 7, which is 1/4 or 4/16. And probability A is 1/16. So if I add 1/16 plus 5/8, which is 10/16, 1/16 plus 10/16 is 11/16, plus 1/4 is 4/16. That's 15/16 plus 1/16. Yeah, this table on the left, set 1 is fine. It adds up to 16/16. On set 2 on the right, there's a couple issues here. Remember, the probabilities can't be less than 0 or greater than 1. So on x equals 1, x equals 2, that looks fine. But x equals 3 is 5/4. That's greater than 1. That's not allowable. And then x equals 4 is negative 1. That's also not allowable because it's less than 0. And you could say, well, if I add it up, 1/2 plus 1/4, which is 2/4 plus 1/4 is 3/4, plus 5/4 is 8/4, minus 1 is 4/4 or 1. You said this adds up to 1. Yes, but the individual components have areas that are less than 0 and greater than 1. So this is why set 2 is not allowed. Now, one thing we're going to be using the rest of the summer here is looking at the standard deviation. And the standard deviation is found, that little u is called mu, is found by the sum sigma of x times the probability of each x happening. Let me go through this. Now, on the top part, what I have here is a score of 1 through 5. This is actually the same scores as the industrial psychologist for those 150 individuals. Remember, 16% scored a 1, 22% scored a 2, 28% scored a 3, 20% scored a 4, and 40% scored a 5. I've taken that same data, that 1 through 5, and their scores, and put it in these two vertical columns here. Now, to find out the mean of these percentages here, I multiply 1 in the x times 0.16. I got 0.16. 2 times 0.22, which is 0.44. 3 times 0.28, which is 0.84. 4 times 0.2, which is 0.8. And 5 times 0.14 is 0.7. I sum that up, and that's what this formula at the top is really stating. The mean of my probability distribution for all these, because remember, we're talking about weighting before, is 2.94. It's close to 3, but there are some different volumes of scores among the different groups. So the mean, when you weight it, and this is what we're doing here, is 2.94. Now, we got to find the variance. The variance we really can't do much with, but we need to find the variance to find the standard deviation. We're going to discuss the standard deviation more in the coming weeks, how important it is in terms of statistical analysis. And basically what it is, it shows the variation between all the data among each other. I'm going to use our data we've been talking about with the industrial psychologist here. And we're just going to keep working on what we had. So you've seen that top table. You've seen the second table. Now I'm going to find the standard deviation. That's why I have the second table from the previous page. And I need to find my x minus my mu, which is basically my mu is my mean. I'm subtract x minus mu to get each of one of those individual components. And that would be 1 minus 2.94 is negative 1.94. In the second row, 2 minus 2.94 is negative 0.94. 3 minus 2.94 is 0.06. 4 minus 2.94 is 1.06. 5 minus 2.94 is 2.06. Each one of those x minus mu's I found out, I'm going to square. So negative 1.94 squared is 3.76. Negative 0.94 squared is 0.88. 0.06 squared is basically 0. It's such an infinitesimally small number. 1.06 squared is 1.12, and 2.06 squared is 4.24. Now I'm going to take that squared number I found and multiply times the p of x, that percentage, the probability of each component from 1 through 5. Remember, number 1, it's going to be passive, they got 0.16 or 16%. So I'm going to multiply 0.16 times 3.76, which is my x minus mu squared, I get 0.60. 0.22 times 0.88 is 0.19. 0.28 times 0.00 is 0.00. 0.20 times 1.12 is 0.22. And 0.14 times 4.24 is 0.59. I'm going to sum that up. That is 1.62, and I add 0.6 and 0.19 and 0 and 0.22 and 0.59. That is small sigma squared. That is the variance. I take the square root of that to get the standard deviation, and the standard deviation is 1.27. So basically, among all 150 individuals, the variation based on the volume of each individuals in each score is 1.27. It is anywhere from 0 to 5. Now, one of the things we can look at is the mean of the expected value. The mean of the expected value gives us the likelihood of an event occurring. For example, we have some raffle tickets here. Let's suppose 1,500 tickets are sold, and you pay $2 each. So, and the raffles are there's a one chance at $500, 4 prizes, one for each, one possibility for each one. One chance to get $250, one chance to get $150, one chance to get $75. So the way we look at this, we got to look at the game. You may win $500, but it costs you $2 to play, which means your net gain is actually $498. And then as you got below that is what's the chance? There's 1,500 tickets. There's only 4 chances. And what's likely getting 500? It's 1 out of 1,500. Same thing with $250 prize. You may win $250, but you had to pay $2, so your net gain is $248. And there's only a 1 out of 1,500 chance to get 250. Same with the $150, where you pay $2 for 148 net gain if you win, and there's only a 1 in 1,500 chance of winning. $75 is $73 because you had to pay $2 to win 75, and you only have 1 in 1,500 chance of winning. And the likelihood of not getting a prize means you pay $2, but you don't get anything, so you're -2. And that's 1496 out of 1,500. And again, if you look at the probability, if I had 1496 plus 1 plus 1 plus 1 plus 1, that's 1,500 out of 1,500. And when I look at this, to determine what my expected value is, I basically multiply the net gain times the probability. So 498 times 1 out of 1,500 plus 248 times 1 out of 1,500 plus 148 times 1 out of 1,500 plus 73 times 1 out of 1,500 plus 2 times 1496 out of 1,500. And when I add all this up, I get -135. So the likelihood that the mean net gain of how much you'll make or lose on this raffle is likely -$1.35.